All right, let's dive into a question that seems simple but is actually a huge deal in data science. How can a model or a test be 99% accurate and still be completely dangerously wrong? Let's break it down. Okay, so picture this. There's a new medical test, and the company says it's 99% accurate. I mean, that sounds amazing, doesn't it? You'd feel pretty confident in that result. But what if I told you that depending on the situation, that 99% number could be hiding a massive failure? So we're going to put this number through what I'm calling a test of trust. We're going to explore exactly how and why that shiny 99% accuracy might not be what you think it is. See, a single number like accuracy can sometimes hide more than it reveals. To get the real story, to figure out if this test is actually any good, we can't just look at the final grade. We've got to peel back the layers and map out every single way this can go, the right ways and the wrong ways. And that brings us to our main tool for the job, the confusion matrix. Now, don't let the name intimidate you. It's actually a super simple but powerful little grid that shows us exactly where a model is nailing it and, more importantly, where it's getting confused. Let's build this thing one piece at a time. First up, we've got the best case scenario for someone who's actually sick. A true positive. This is a direct hit. The test says you've got it, and you do. Perfect. Next, there's the false positive. This is your classic false alarm. The test flags you as sick, but you're perfectly healthy. This is the kind of error that leads to a ton of unnecessary stress, maybe even treatments you never needed in the first place. And then we have what is almost always the most dangerous mistake, the false negative. This is a total miss. You are sick, but the test says, nope, you're fine, go on home. In medicine, this is the error that can have catastrophic consequences, letting a serious illness go completely unchecked. And finally, to complete our set of 4, we have the ideal outcome for a healthy person, a true negative. The test gives you the all clear, and it's right. You're healthy. Phew, what a relief. So you take those 4 outcomes, pop them into a simple 2x2 grid, and there you have it, the confusion matrix. It's just a way to see what actually happened versus what the test predicted would happen. In one quick look, you can see every win and every loss. Okay, so now that we have this map of all the outcomes, we can start calculating some really useful metrics. Metrics that tell a much richer story than that one single accuracy number ever could. First, let's just officially define accuracy. It's the one everybody knows. You just add up all the times the test was right, the true positives, and the true negatives, and you divide that by everything. It's just asking a simple question. Overall, what percentage of the time did it get the right answer? But this gets us right back to the heart of the problem, doesn't it? What happens when some mistakes are 1,000 times worse than others? What if telling a sick person they're healthy is a much bigger deal than telling a healthy person they're sick? Suddenly, just being right overall isn't good enough. And that idea leads us straight to precision. You can think of this as your no false alarms metric. It answers a very specific question. When the test did raise a red flag in, say, sick, how often was it actually correct? High precision means when the alarm goes off, you better believe it. And its partner in crime is recall. I like to call this the leave no one behind metric. It asks a completely different question. Of all the people out there who were genuinely sick, how many of them did our test actually find? High recall means you're casting a wide net and you're not letting cases slip through the cracks.
So you can probably feel the tension here, right? It's a constant balancing act. If you make your test super sensitive to catch everyone, high recall, you're probably going to get more false alarms, lower precision. This forces us to make a critical choice for every single problem we're trying to solve.
Think about it this way. For something like an email spam filter, you want high precision. A false positive, a really important email getting sent to spam, is a disaster. You'd rather let a couple of spam emails through. But for our disease detection test, you demand high recall. A false negative, missing someone who's sick, is the absolute worst-case scenario. You'd happily accept a few false alarms to make sure you find every single true case. Okay, let's bring it all home. Let's go back to that 99% accurate test we started with. But now let's add one final crucial piece of information. The disease it's testing for is extremely rare. And here's the trick. Here's how that 99% number can fool you. If a disease only affects, say, 1% of the population, a test can achieve 99% accuracy by doing something incredibly dumb. It can just predict healthy for every single person it sees. Think about it. It'll be correct for the 99% of people who are healthy, but what's its recall? 0. It will find 0 sick people. Accuracy makes it look like a star performer, but recall reveals it's a complete and utter failure.
And what's really cool is this isn't just some abstract theory. For anyone working in data science, you can see how this plays out in the real world. A simple line of code like this one from a common Python library is all it takes to measure not just that misleading accuracy score, but the precision and recall that tell you what's really going on.
So look, if you take away just one thing from all of this, let it be this. There is no such thing as a single best metric. The real skill is to stop and think deeply about your specific problem and then choose the metric that actually aligns with what you care about most.
So I'll leave you with a final thought experiment. A self-driving car is using a model to detect pedestrians. Now, which error is worse? A false positive, where the car brakes hard for a plastic bag it thinks is a person, or a false negative, where it fails to see a person crossing the street? You know the language now. Which metric, precision or recall, is the one that actually saves lives? Thanks for joining me.